Coded. So coded.
Hey! Yeah, hope you sleep well. So first talk of today is Andy Campbell from GitHub, and he'll talk about low-level programming. So hope you all wake up now. Welcome, Andy.
It's working now? Yeah. Okay, so over the past couple of days, people have been asking me what this talk is about, basically. And I sort of have had thought in my head that I've always called it systems programming and Ruby systems programming. But that makes it sound like this is a talk about how to program a system or like all these low-level things. And it's not really so much about that. It's much more about just knowing sort of the tools that you use and the building blocks that build up the systems that you already program in, all the application code. So that said, we are talking about systems programming a little bit here. So what does that even mean? What are we talking about in systems programming? This is a definition from Wikipedia. It says to operate and control the computer hardware and to provide a platform for running application software. And I really like this definition because it kind of breaks it into two pieces. First, we're operating the computer hardware. So this is something very low level. It's interfacing with the hardware itself, the memory, the disk I/O, the monitor, the sound card, anything like that. But we're also providing a platform for running application software, which means that this is the kind of software that other software runs on top of. This is nothing that a user's ever going to see directly, which I think is kind of interesting. So we're talking about application software. This could basically be anything, right? This could be an iPhone app. This could be a game, a video game, something runs on a set-top box. But I'm going to talk about web software because I think most of us are web programmers. I'm definitely a web programmer. I mostly write Ruby on Rails. So I'm basically going to be talking about the software stack between the kernel and the hardware all the way up to sort of the bottom of the application software that we write, so like the bottom of the Rails app. This is the stack that I'm going to talk about. We're going to start all the way at the bottom and build our way up. So we're going to start at the kernel, where we're going to talk about how that interfaces with the hardware. System calls allow you to call into the kernel. File descriptors that we use to talk about anything that looks like a file in the system. BSD sockets, how we do network programming, and then a little bit about HTTP, and then at the end we're going to talk a little bit about a full HTTP server written in Ruby. In general, this should apply to sort of any Unix system, but anything specific that I talk about is going to be geared towards Linux, because that's Linux x86. This is kind of low enough level that it actually depends on which system you're talking about, and some of the things actually depend on what architecture and hardware you're talking about. So, starting at the bottom. First we have the kernel. And the kernel's the thing that runs the lowest possible level in the system. This is going to be interfacing directly with the hardware. And kernel programming is actually quite different than systems programming. They look kind of similar. It is still providing that platform layer for other code to run on top of. But the nature of how you do that is very different. You're running inside the kernel. You're mostly writing device drivers and dealing directly with the very lowest level of hardware. The systems programming that I'm talking about is sort of one level abstracted above that. This is a very basic diagram of how a computer works. At the bottom you have the hardware. So this could be anything from the hard disk network stack, memory management, I/O of any kind, anything like that. In the middle there you have the kernel layer that's providing the interface to all that hardware. And at the top, this is where anything you think of as a program runs. So any programs on the computer, anything that's actually doing anything real, right? So your code, pretty much any code that any of us write, is going to live in that top green layer. So your code, we run this in what's called user mode on the system. And the things that you can do in user mode are really, really limited without calling into the kernel. So there's kind of two things that I think that you can do in user mode. One is what I call math. So this is anything that's modifying stuff that you already have access to. So this could be as simple as actual arithmetic, where you're like adding numbers together, modifying strings, concatenating strings, or like doing crypto crazy math, like actual math. But the idea is that you have things already, and you're basically just modifying them locally. So you're running commands on the CPU, but you're not getting anything from users or sending anything out, right? And the other thing you can do is you can access memory. But this is only the memory you've already been given access to by the kernel. So you can read and write from memory and sort of keep track of stuff, but you can't allocate new memory. So what's not here? It's like everything, right? You can't listen on the network, you can't write files, you can't put things onto a display, you can't allocate new memory, you can't fork processes, you can't even exit, you can't quit your program without calling into the kernel. So the kernel, on the other hand, if you're running code in kernel mode, it can literally do anything and everything. Like there's nothing it can't do. Code here can access any memory, read and write, it can modify processes, it can talk to any device, write it anywhere on the file system, it manages the file system, everything like that. So because we have these two modes, and we obviously need to do some of the things that the kernel can do, you might imagine that the way this works is that you kind of chug along in user mode, and then you need to do something that goes into kernel mode, and you switch contexts. So you need to write a file, and then you switch into kernel mode, you write a couple of lines of code that then write that file, you switch back to user mode and continue on your merry way. This is not how this works at all. Anything that runs in kernel mode, because it can access anything, you don't get to write code there. You don't get to run code there. All you can do is ask kindly for the kernel to handle things for you. And the mechanism we do that with is called system calls. So system calls are basically how everything gets done in a computer. This is how most things happen. Again, we have our diagram here with user mode and kernel mode. The hardware's down there at the bottom. And your program runs in user mode. And then through this interface that kind of allows you to access into the kernel, you can make calls into the kernel. You can see what kind of system calls your program makes with this strace command. This is on Linux. There's similar ones on Mac and BSD and things like that. You give it the process ID of the processor you want to inspect, and you can see every single syscall that this makes. This is stracing one request locally on the Gist app. I work at GitHub, so this is an app that I work on. You can see that it does kind of all kinds of things here. So these are all the syscalls on the left here. There's a bunch of obscure ones that I don't really understand that well, including sigproc mask and things like that. But there's some more sort of normal ones here too. We have close, accept, get parent process ID, send to. These are kind of familiar, maybe. I'll talk a little bit more about all of these later. So the syscalls come in much faster than the frame rate of the video. Over the course of that request, there was 120,602 calls. So almost literally everything that we do happens via this mechanism. You don't see it because it's wrapped in these other APIs, but basically everything we do goes through the system calls, especially with web apps where we're dealing with the network and file I/O and databases and things like that. So because everything we do goes through system calls, and we know that we have 120,000 requests, or system calls that go for one request, you might imagine that this API is really, really large. And at Linux, at least, it's really small. There's only a few more than 300 system calls, period. And syscalltable.s is the actual assembly code that is in the kernel that lists all the system calls. You literally cannot have any beyond that. If it's not in that table, it doesn't know what to do with it. So how do we make system calls? I was talking a little bit before about how we switch modes and call into the kernel. This is the actual assembly. This is x86 assembly in Linux. This is for the open system call. There's a little bit of formatting there. There's supposed to be spaces after the moves. But so this is the open system call where you open a file to a path and you get a file descriptor back that you can talk about. Every system call has a number associated with it. Open happens to be number 5. That's what that table shows. So you move into the EAX register number 5. You put the args and corresponding registers there and beyond. If you have more than 5 or so arguments, you have to use a different method, but that almost never happens. And then you trigger this interrupt. So this is triggering a software interrupt with the code 80 in hex. And that fires the interrupt handler in the kernel. The kernel looks up what the 80 hex syscall handler or system handler is, interrupt handler, which happens to be the syscall handler. The syscall handler looks in the EAX register, sees what number that is, looks it up in the syscall table, and then executes the code. But you can see how you're actually performing an interrupt, so your code is not running anymore at all. It's all on the kernel. You don't get to do anything here. And then eventually it'll return back to you, and you get back the results. So another kind of fun fact here, of those 326 system calls that exist in Linux, 65 of them are implemented as the sys-ini syscall, which stands for not implemented. So the way that the syscall table is built, it has to be linear, it's complete. So if we deprecate a syscall or reserve one for future use, or one's implemented on one platform but not another, you still have to fill in the blanks. So 65 of them aren't actually implemented at all. They don't exist. There's only like 260 left. So Linux is actually really small with its syscall table. Other operating systems are much, much larger. Windows, we don't have this file, so we can't grep for it and see how many there are, but it's widely rumored or assumed that there's many thousands of them. I find it really interesting that basically with 260 syscalls, we have as much power in the Unix world as you have to have thousands to do in Windows. Kind of like the smaller API. So I'm going to talk a little bit about file descriptors next. All of those syscalls, or many of those syscalls, deal with reading to, writing from files, and things that look like files. And in Unix, they go by this philosophy where they call everything as a file. This is not quite true. Some operating systems take this much, much further than Linux does, or Unix does. But most things are treated as files. Anything you're going to read